Hi, how's it going? My name is Carl Diaz. I am with the Learning Resources Center at the University of Colorado, Denver. Today we're going to be solving a problem, a pretty complicated one with two boxes attached by a rope. I have the physics checklist written down here. Keep in mind I won't write it for every video, but we're going to use it. I want you to understand how to use it to solve any type of problem, especially one like this. Typically my problems are all the way solved out for us because I'm trying to explain them to you so that you understand how to solve them. You don't need to see me writing things, but sometimes it's important to see some things. I want you to watch me make my free body diagram, watch me write the equations, things like this. So that's kind of what's going on here. So let's get started. So the physics checklist, right, going off of how to, right, this really walks us through how to solve any physics problem, doesn't matter which one it is or what semester we're in. I'm gonna go ahead and follow this. So the first thing obviously is important to read the question. So we got two boxes are connected by a rope with an ideal pulley, right, which an ideal pulley means there's no friction associated with it. Box 1, and it has a mass of 10 kilograms, sits on a surface with a mu of 0.17. And box 2 has a mass of 100 kilograms. What is the acceleration for box 1 and box 2 as they begin to move? All right, so again, remember acceleration, big word, big fancy word. It just means rate and change of motions. In this case, it's the rate of change of motion for these boxes is what they're asking for. So again, don't think acceleration because we don't know what that word is until much later in our physics studies. So try to think of it as the rate of change in motion so that you're separating it from force. Okay. Now we just need to write down our givens, which is very, very, very easy to do. Probably should get a few more colors here. So we'll go ahead and do that. And that's just very straightforward, just boxing off your givens and writing down, just looking at your question. They give us box 1, right, which is M1. Tell us that's 10 kilograms, right? We know that there's a mu. I'll kind of write it down here because I know I got a second mass to write in there. I just like them together. It doesn't matter. You don't have to do it like this. And box 2, which is M2, right, is equal to 100 kilograms, right? That's about all we are given. We know the pulley's ideal, but there's nothing in our givens that we can really indicate that. And then you always want to put the question. So there, we're asking for the acceleration here, right? So there we go. Step 2 is done. Free body diagram. All right, so this part is probably the most important because again, you're gonna have an equation sheet, you're gonna be given equations, right? Whether you're in the calc base or the algebra base, you're gonna have the equations is the thing. You're gonna know how to get them or derive them. So that's not the problem. The problem is how to fill them in. And filling in those equations comes from your free body diagram. That's why it's so important to have them. Why your professors stress them. You might feel it's so silly to do, but that's why we stress them. It's important. Okay, so free body diagram is just the forces, right? We can indicate change of motion and things like this on there, but again, the free body diagram is mainly looking at the forces on the objects that are in question here. So we have these two boxes, right? We know this is, and we can kind of, right, we want to put in some coordinate system here so we know what's positive and what's negative, and I didn't do anything weird here. Positives that way, right? We want to know that this is M1, we want to know that this is M2, and we want to go ahead and then draw those forces. So we know any box that has weight, right, when it's applied to that weight to a surface, the force that pushes back on it, right, Newton's third law is going to be the normal force. So we have weight of the box and then the normal force, which is from the surface pushing back on the box. It's there all the time, right? Newton's third law. And then we are told that there's a mu, which means there's friction, right? This sits on a surface with a certain amount of friction, so we know it's there. So we want to write in friction. You don't have to put a mu. Friction is the force there, so that's what we should be putting in. And then we know that there's tension here, right? And we also know from what we understand about tension is the tension that runs through here is going to be the same. There's not a different tension here versus tension here, so you don't have to put T1 because this is all the same tension. Now, if it was going through another pulley, or something like this, that's where things change, okay? But right here, this tension just through this one pulley right here, that is all going to be the same. So we can just write it as t. I want that vector to be longer, right? Because it's going to move this way. We know this weighs more, so obviously when it's released, it's going to move this way. It should be larger than this vector, right? This is important to understand because that's what vectors are. It's drawing them correctly. So if you don't draw them correctly, you might be marked off. I can almost guarantee you will, because we focus on this a lot. So as we just said, the box is going to move this way. So we know there's going to be some sort of motion, which is my velocity, and then some sort of change in motion, because we know it's starting at rest, which, by the way, bringing that up, we probably can add that to our givens, right? We know its initial velocity is 0. It's kind of good to put those things in. We may not need it, right? But it's good to put those things in. So yeah, let's add that. We know it's going to start at rest, and it's going to get some sort of velocity because of the rate of change in motion of these boxes. All right. So that's pretty much it for box 1, right? Now we want to move on to box 2. Now this isn't sitting on a surface, so there's no normal force, but the tension is here, right? Now if the tension was more than this box, the weight of this box, the box would be moving up, right? And we know this with what we see from elevators. If the tension's less than this weight of the box, it's going to be less, and the box will be moving down. And then they could also be in equilibrium and equilibrium situations or balance, and we can talk about that in a different video. So we know that this thing's moving, right? So let's put and it has weight. Let's put the weight here, and then we know that there's a certain amount of tension up, and again, it should be a shorter vector because this is the weight is moving down. Okay, so again, this tension's larger here because it's moving this way. This tension's smaller here because this is making it move that way. Alrighty, and again, we know that these boxes are moving down, so they're going to have velocity and acceleration in that direction, and we want to just draw all those on there. Again, those aren't forces, but we draw those off to the side. They shouldn't be connected to the box because they're giving us information about what's going on here. It's good to know. All right, so that's it for the free body diagram. You don't have to do anything else besides that, but it's one of the most important things to have, and you're going to see why. All right, so concepts. What are the concepts here that we can use, that we understand? Again, physics is a science class, so we want to apply the science here and things like that. So what can we see from our free body diagram? It tells us a lot, right? We see some balance, right? This box is balanced on this surface because it's not moving up or down or breaking through. So the box is balanced. That's Newton's first law, equilibrium. So we know there's that concept, right? We're going to have that concept applied here. We also know that there's acceleration, right, for these two boxes. This one in the X, this one in the Y. But we know that it's there, which means there's some sort of rate of change in motion, right, which is Newton's second law. So we know we have Newton's first law and Newton's second law applied here. That's how you know that. And we know the equations that go with them. We're going to write them down here in just a second. Okay, so just keep that in mind. We're going to look at that, all right? And this box doesn't have any forces in the X direction, so we'll kind of talk about that here in a second as well. So, all right, so let's write down the equations that match the concepts, and we want to make sure that we're associating it with the proper direction and everything like that. So we know box 1 has two forces. It should have a sum of forces in the Y and X, because it has forces in the X and forces in the Y. We see that the forces in the X here, right? Acceleration, that's where the rate of change of motion is. So that's where Newton's second law is going to apply. The concept of a rate of change in motion, right? The concept of some sort of net force. Remember, that's Newton's second law. There's a net force here pulling this box. There's a net force here. So that's Newton's second law. We know because it's moving and starting to move from rest. So we want to write that down, right? Or sum of forces, oops, not that, in the X are going to be equal to Newton's second law, right? And we would put in the sign for acceleration if it was negative, but it's positive, so we can say like that. Alrighty, and then we know also that the sum of forces here, and I'm going to redraw this line, for the Y are going to be in equilibrium. So let's go ahead and do that, and that's sum of forces in the y. And again, we want to label this up as M1. This one's going to be equal to Newton's first law, so it's just 0. We'll start adding in the M1s when it's appropriate, but it's important to do that, okay? You want to make sure that you are putting in M1 and M2 because we want to know the difference there. All right, and then for box 2, right, we know that there's no balance. This is just having a rate of change where there's some net force pulling it down, right? There's no forces in the x direction, so we're going to have, right, our sum of forces in just the y, because it's the y direction, right, are going to be equal to Newton's second law, because again, it's moving. There's a rate, not just because it's moving, because you could be moving and still be in Newton's first law if it's constant velocity. But we know we're starting from rest and starting to move, so there's going to be change in velocity, a rate of change in motion. And that's how we know that. And it's in the negative direction, so let's put that, negative MA, and let's make sure we put 2 there. Okay, so those are great. All right, so now we want to fill in the equation from our free body diagrams. This is super important. Okay, this is why your free body diagrams are important. So let's do that. Let's start with the x direction, right? So we know tension, right, is in the positive x direction, so we want to write that, right? And then we know that friction is in the negative x direction, so that's why it's going to get the sign that it does, okay? That is literally why it's getting the sign that it does, no other reason. Okay, it's in the opposite, or it's in this direction. Okay, if we wrote positive x over here and negative x over here, tension would be negative, friction would be positive. The math would be the same, right? But that's why it has the sign. It's important to understand why it has the sign, okay? And then we know that's going to be equal to MA. All right, now we know that we weren't directly given friction, right? So we want to make sure that we, again, turn friction into what we know. We know friction, right, from the equation we were given, is equal to mu times the normal force, right? So we want to change friction to that, because that's what we were given. That's what we know. Those were the given parameters of the question. And then we can finish it off. Again, this is just the sixth step here. We don't want to do too much more here until we know what we need to do. Okay, so that's good for now. All right, now we want to do the sum of forces in the y. Okay, so that's just going to be the normal force, right? And it's positive, and the weight is negative. Okay, so that's going to be minus mg. Again, that's why it's getting the sign that it is, because of this. If this was positive, we make that positive. And is equal to 0. We know because of the Newton's law, okay, the balance that's here. That's why we're writing that. That's why we can end it with 0. If there was just one force on this side, that's okay. I see students sometimes being uncomfortable if this was just mg, let's just say, okay? They're uncomfortable with writing something like that, but there's nothing wrong with that, okay? You're looking at your free body diagram to fill this in. There's no questions. You shouldn't be asking yourself, well, what do I do now once I write this in? You did it in the free body diagram. The thinking should be done. You're just copying things down from your free body diagram into these equations. That's all you're doing, very, very simply. Okay, so the next thing we can see here is that we need our normal force, right? We're directly given our normal force, but we know this equation gets it for us, right? So let's go ahead and do that, because we want one good equation here in a second. So before we move on to that step, let's go ahead and fill this in. So here, for the second box, right, we want to then fill in the equation from our free body diagram. We just got these forces. Tension's positive. Tension's going to go up, positive. Weight is down, negative. I'm going to write it as such. This is M2. Right, and then it's equal to, and that negative sign stays, don't lose it. Okay, A. All right, and so we have some good equations here, right? So we want to kind of start putting some equations together based off what we need. We know we need normal force. The other thing that we know, because it's quite interesting when we start to look at these equations, is there's acceleration. There's acceleration. The accelerations are the same for these two boxes. You should know that. They shouldn't be different. Even though there's asking for acceleration twice, it's a trick. It's trying to make you think, oh, are they going to be different or something? They're not. You should know that they're not. Okay, they're connected. All right, so the acceleration is going to be the same. Even if the forces were changing, the forces should be changing the same on them. They weren't, that's a totally different story. We're not talking about that. Talking about these two, the force on it, the net force on these boxes are the same. Okay, so if the net forces on the boxes are the same, then the acceleration is going to be the same. So we have it right here. The thing is we don't have to, well, for this equation, we don't have normal force, and we know we can get it. We'll talk about that in a second, right? But we don't have tension. We weren't given the tension, right? So because of that, we have to kind of think a little bit deeper when we go to put our equations together, because we kind of need a few things here. We need normal force, we need tension, right? If we can figure out the tension, we can get the acceleration. If we were given it, we could solve this equation for acceleration and we'd have acceleration because we know the tension's the same for both of them. We know that, all right? And acceleration would be the same. So keep that in mind. You want to look at what you were given. Sometimes this question could be given very simply. Sometimes it could be given very complicated, all right? So here was a little bit more complicated. So we want to put these equations together, right? Because we know we need the normal force in here. So we want to do that first to make sure we have some good equation to work with here. All right. And that's going to be m1g equals m1a. All right, so that's these two equations coming together, right? I didn't put the normal force in here because we know what it is. And we know what m1 is. We know mu, we know g. Right? Okay. And over here, right, so we're kind of looking at these two equations saying, okay, well, what do I do next? I have two good equations. Well, as you should have learned in algebra, we could solve either one of these equations for tension, right? We can put it into the other one and then solve for acceleration, right? And that's exactly what we want to do here. Again, we weren't given the tension, right? If we were given the tension, we could just put it into this equation, get the acceleration, right? Put in this equation, get the acceleration, but we weren't, but we can get it. All right, so what we're going to do is we're going to move over here and put these two equations together, right? So let's go ahead and first solve this one. You could solve either one for tension. It doesn't matter which one. I'm going to solve this one for tension. If you want to solve that one for tension, you can. All right, but we want to put them into each other. Be careful not to, I see a lot of students, even though it's asking for what they're asking for, acceleration, I see a lot of students wanting to solve for acceleration. Don't do that. When you do that, you're getting rid of acceleration. Okay, and when you get rid of acceleration, you won't have it to solve, right? Because you're going to solve this for acceleration, put it in there, then you're left with just tension, all right? They're asking you for tension, and you weren't given acceleration. That's exactly what you want to do, all right? But you weren't. All right, so M2 comes over and becomes positive over here. Again, you don't want to show that work. Just write it, okay? M2, right, becomes positive. This stays negative, so that's minus M2a. So now we got two good equations. Let's put them together, right? We have the first equation, right? T minus mu m1g equals m1a, right? And then we have the second one, right? Which is T, let's kind of just do this, equals m2g minus m2a. Okay, so we want to put these two equations together. We want to put tension in there, right? We want to put these two equations together, putting this into that one. So let's do that, right? So let's start with it. M2g, right, minus m2a. Okay, we've got all of the tension in there, so now let's just put the rest of this equation. Minus mu m1g equals m1a. All right, so now we got all these, we got a nice good equation. We've put our equations together, right? It's a long process, it can be a long process. Sometimes you won't have to do it. This time we had to do it a few times, okay? So we're still doing that, right? We kind of got a nice good equation. Now we're solving for acceleration now. The rest is math, right? Well, it's been math from this point, but it's very, very algebraic from this point, right? So the next step we'd want to do is we want to bring acceleration on the same side, right? We want to bring, everything needs to be on the same side. So let's just bring that over. Everything else can stay on this side. We just need to bring M2A over, right? So M2 2g. All right, that's going to disappear. It's going to become positive over here. Again, I'm doing this because this is what your professors want you to do. You got to be at this point already. Shouldn't be plussing, adding over here, adding over here. No one needs to see that. Okay, we're in college. All right. And, right. So we have this, and this is going to come over and become positive. So M1A, and that's going to be plus now M2A. All right, well, we got acceleration on the same side now. All right, so what do we do next? Your favorite thing your professors love to do, which is factor A out. Okay, and to save some room here, I'm just going to go ahead and start doing that here. So you want to write A out here, which means we're going to bring this A is going to come out, right? So all we're going to be left with is M1 and M2 in here. All right, so M2G minus mu M1G equals, now we're just going to have M1, let me write that a little bit bigger, M2G minus mu M1G equals, and then we're going to have M1 inside plus M2, and then the acceleration has been pulled out. Now we can just bring M1 plus M2 underneath this, and acceleration's by itself, and we're done. It's that simple. Yay, we're done. All right, 2g minus mu m1g. And again, this is why it's important to keep track of your m's, because you want to make sure that when it's time to put the numbers in, you're putting the correct numbers in there. All right? And this is going to be equal to a. So there we go. There's our acceleration. Okay? There's our acceleration. Pretty straightforward. Pretty simple once you get to that point, I guess, or once you see it all. But remember, there's a saying in physics, the logic is very easy to follow. It's when you have to come up with it on your own is where it gets difficult, right? So just keep that in mind. You watch me do something here, but it's something that you can do on your own. Just make sure that you're thinking about it the way you are. You're doing the concepts, right? So we put the equations together. Now you'll solve. You'll go ahead. You can throw the numbers in at this point to save time on this video. I'm not going to do that, but you can put these numbers in there, right? And hit enter on your calculator, and you have the acceleration. All right? So thank you so much for watching. I appreciate it. I'm super proud of you. Keep up the hard work. Again, watch this video multiple times if you need to. And I'll see you on the next one.